In the previous video, we saw that applying a forward bias to the p-n junction lowers the barrier against majority carriers crossing the junction, allowing minority carrier injection. Let's look at the injected charge carrier profile on a linear plot instead of logarithmic. The injected electron concentration at the junction is 10 to the 12 per cubic centimeter. The electrons recombine with the majority holes in the p-type region. The electrons fall off exponentially as they go deeper into the p region. Like a radioactive element, the rate at which electrons disappear by recombination is proportional to the number of them present. The x-distance decay constant is called the diffusion length, or L sub n. The length depends on the electron diffusion constant and the average electron lifetime. One diffusion length can be microns to hundreds of microns long, whereas the depletion region is a tiny fraction of 1 micron. That's why the depletion region is too narrow to see in this diagram. On the n-type side, holes are injected and recombine with majority electrons. Because holes and electrons have different properties, their diffusion lengths are also different. The non-uniform carrier concentrations result in diffusion currents, which are proportional to the slopes of the concentration curves. In the p-type region, for example, electrons diffuse toward the right. This graph shows the current I through the semiconductor in amps as a function of x. The total current consists of two components, holes moving toward the left and electrons moving toward the right. Both components contribute to current toward the left, electrons having a negative charge. The total current is constant across all values of x, which is a requirement of Kirchhoff's current law, so the electron and hole currents are complementary, adding up to the same constant value. On the far left, all the current is due to electrons. As the electrons approach the junction, they start to recombine with the holes injected from the other side, so the electron current decreases as the hole diffusion current increases. Electrons injected past the junction soon recombine with majority holes, and the electron current drops to zero in a few diffusion lengths. On the far right, all the current is due to holes. As holes approach the junction, they recombine with electrons injected from the left side. Holes injected past the junction soon recombine with majority electrons, and the hole current drops to zero. Now let's return to the linear plot of injected carrier concentrations. We applied 0.48 volts to get a peak electron concentration of 10 to the 12. The diffusion current is proportional to the slope of the graph. If we lower the voltage by 0.06 volts, the carrier concentrations, diffusion current, and total current decrease to 1/10 of what they were, and vice versa. Now we go back to the log plot of the majority and minority carrier concentrations. Reducing the voltage to zero gives us the original flat profile. Applying a negative voltage has the opposite effect, reducing the minority charge carriers near the junction. This is called minority carrier extraction, which is important in bipolar junction transistors. In the next video, we look at the IV characteristics of the p-n diode and see how the p-n junction can operate as a solar cell or light-emitting diode.